Okay, so my name is Han, and I'm the founder and CEO of Jina.ai. So we're also based in Berlin, and actually in the starting from 2020, I set up this company, and the first office is very close to the Deutsche Dom. So there was a Radisson hotel which has a lot of fish, and then eventually they just get out. This accident, and we were there before, right? And very close to that place. And then we switched to several other places. One time was in Leipzigstraße, just very close to here. And right now we are in kind of in between Neukölln and Kreuzberg. In the Umspannwerk. So that office was previously owned by Google. Not owned by Google, it's actually renovated by Google. But then under the protest of Berlin's leftism, and then this Google just withdraws all the things. And then but this was a very nice office. Anyway, so today I'm going to talk about our embeddings, open source embeddings, and actually I have a very good connection with LFAI. I started to work at LFAI since not start to work at, I start to have this connection with Linux Foundation AI back in 2018 when I work at Tencent, right? And I was representing Tencent to do open source AI in the Linux Foundation. And so that's where I start this kind of official open source journey, right? And later I found this company which is also focused on commercial open source software solutions in 2020, especially focused on multimodal AI, neural search, embeddings, this kind of technology. So right now our primary focus this year since 2023 is prompting and also embedding, right? So there's Clement is the CEO of the Hugging Face, also give us some endorsement about, okay, so this guy knows about embedding technologies and so on. So we have some flyers there, so if you want to know more about us, so feel free to look at this very well-designed threefold flyers there, right? So today's agenda, I will, I guess not everybody know about embeddings, I will give some technical detail, not technical details, but kind of the introduction of embeddings to help you understand, okay, so first of all, why do we need embeddings? Secondly, what is considered as a good embeddings, right? And then, I will tell you about how great this embedding, like a Jina.ai embeddings is, right? And also, of course, how to use it, right? So, okay, so let's come to the first section, so which is basically I'm assuming that nobody come here for this kind of embedding, right? Because this is also kind of embedding that also strongly related to Linux Foundation, right? So because under Linux Foundation there is also a chapter or a section which is all about embedded open source, right? Linux itself is of course used in a lot of embedded edge device. So sometimes I talk embedding in the open source summit, and under Linux Foundation people get confused that, oh, what embedding are you talking about, right? Then after 5 minutes they say, okay, so I'm not really interested in this embeddings, right? I'm the hardware guy, so I'm not really interested in this software embedding stuff. Right? So this happens several times, so that's why I put the disclaimer here. And especially interesting that this summit often has the same time as the OSS summit in Europe. Right? So there's OSS summit Europe plus embedded summit, right? So that's why this kind of just makes everything very chaotic, right? But it's a good way to make friends, right? So if you ask ChatGPT what embedding is about, right? So it will answer says, oh, embedding is a vector that represents something like some objective. So this vector can keep the original things, the features in a way that it can be measured and compared, right? Which is really not very clear, right? But what we get from here is, okay, so it looks like embedding, first of all, embedding mathematically is a vector, right? It's a vector in the kind of 2D, 3D, or even higher dimensional space, right? It's a vector. And then it is used to represent some real object, right? So that's enough for us to carry on, to move on to the to the next part, right? So let me give you a very concrete example. Since we all live in Europe, so let's use these common coins of euros, from 10 cents to 2 euros, that, as an example, right? So we have a lot of coins, which you can measure the coins by their diameter, thickness, and weight, right? And this, if you put that into a table, then you get this kind of multi-row tables and 3 columns. That each column represents kind of one characteristic or feature of this coin, right? And then in this case, you basically represent each coin, a real-world object, into a 3-dimensional vector, right? That's the embedding. That's a very, very trivial embedding that everybody should understand, right? So if you put that into a little bit untrivial, like a presentation, you don't put that into a table, you put that into a 3D, right, Euclidean space, then it looks like this, right? So you basically kind of create 3 axes orthogonal to each other, right? And then you put the dots correspondingly in this 3D space. Then you get this kind of 3D space, right? So once we have this embeddings, or once we represent all these coins into 3D space, what can we do, right? So actually we can do a lot of things. We can do classification. We can classify the coins by their let's say by their value. We can do like recognizing whether the coin is a real coin or fake coin. All these kind of things, right? So we can train classifier. We can do a lot of downstream tasks. So this basically summarizes the design pattern in many machine learning applications. First of all, you represent something from real world into vector space, right? And once you have this vector representation, you train a machine learning algorithm on top of this vector representation. And eventually, you use this trained algorithm on some new kind of things or vectors, right? And so let me summarize. I think that's basically enough for the embeddings basic stuff, right? So let's summarize the terminology here, so people sometimes often get confused here. So sometimes we say, oh, this is embedding, right? We use it as a verb, right? So for example, we say, oh, we embed something into a high-dimensional space. So in this case, it's a verb, right? And if we add like a plural embeddings, this usually means a vector, like a set of vectors, right? It says we get a set of embeddings, that represents a coin, right? And so downstream task is usually when we train some machine learning algorithm on top of those embeddings to accomplish, let's say, classification, retrieval, recommendation, this kind of task, right? Okay, so that's kind of the terminology and very kind of foundation of embeddings, right? And then the natural question is, okay, so what is a good embedding? So we have seen we can represent the coin using 3 dimensions, right? So diameter, thickness, and also weight, right? But is this a good embedding, right? Well, it depends usually it depends on the downstream task. We will come to that. But there are certain principles that you can follow to determine whether your embeddings is a good embeddings or bad embeddings, right? So first principle is, the similar items should position closely together. So let's go back to the coins case. So we see that so on the right corner, you have all this high-valued coin, right? So how do we define high-valued coin? So basically, this coin is the coin that you can use in the supermarket to get the cart, right? To get this cart. These are high-valued, right? Right, and huh? Yes. And so those are the coins that, if you steal the card, and ID card will just say, yeah, but they give us like €2, right? Something like that. And so these are the high-valued coin. And then unsimilar items or dissimilar items should position far apart from each other, right? So those kind of low-value coins, they should be in the space, in the Euclidean space, they should be far away from the high-value coins, right? So these are the 2 basic principles when talking about what is a good embedding, what is a bad embedding, right? And then the third principle is a little bit confusing, but it's mathematically very sounding, right? So believe me, right? So it says the embedding space must exhibit continuity and gradual transitions, right? So, and people get confused what exactly is continuity and gradual transitions, right? So this is continue and gradual transition. This is not. Right, so this is a way if you visualize the embedding space, right? So you can basically immediately see that, okay, so there are some embedding space are kind of smooth everywhere, some embedding space are very kind of jittered everywhere, right? So what does that mean? So that means in the smooth embedding space, if you follow the semantics, right? So let's say in this case, our semantic is the value of the coin, right? So if you follow the semantic, right, the value of the coin, you can draw a relatively smooth line, right, a smooth curve, follow the landscape, right, on the embedding manifold, right, and then from the lowest coin to the highest value coin, right. So it's the journey there, the journey that you travel from the lowest coin to the highest value coin is relatively smooth. Right, but let's say if we consider random 3D mapping, so we still use this we don't use these 3 diameters of weight, thickness, this as a feature of those these coins. We just randomly project those coins into this random 3D space, right? And then we follow the semantics from 1 cent to 5 cent, 10 cent, and then eventually to €2. You found that, okay, so this journey is very bumpy and recursive, and eventually it's just very messy, right? So this is basically what does this continuity and gradual transition means intuitively. Of course, there is a mathematical definition, but we don't have to go through in that. Right? Okay. Okay, so the next one, there's the fourth principle. It's also very interesting. It says embedding space should be dimensionally adequate, right? High but not too high. All right, so which is also kind of like, found your inner peace stuff, which you don't understand what it is, right? So high but not too high. So then the natural question is, okay, so it's high but not too high, but should be high enough, right? So is this 3D, then does that mean the 3D embedding is better than 2D, or ND embeddings is better than N-1 dimensional embeddings, right? So in general, the answer is yes. Higher dimension space is always better. If you can represent an object into a higher dimensions, let's say 1,000 dimension, 10,000 dimension, then it's theoretically just better, right? This is because in the higher dimensional space, data are more easier to separate, right? So let's look at this example, right? So if we have this kind of 2 classes, each cross here just represent a data point. And if we map this data point into 2-dimensional space, there's no way to linearly kind of separate these 2 classes, from the separate the red points from the blue points. There's no way in 2 dimensions, right? But if we somehow map this in the 3-dimensional space, then we have more freedom to draw the line, right? Well, in this case, it's not called the line, but a plane, right? So in this case, it's very easy to separate these 2 classes. Why I use this separation or classification as an example? Because in the end, a lot of machine learning algorithm, optimization algorithm can be boils down to the classification, to this hyperplane join stuff, right? So in conclusion, that means higher dimensions gives you more representative power, and it's easier for you to train to have a good performance on downstream task, right? Okay, so let's look at another example, right? But of course, we know that there comes a cost, right? So it cannot be just infinite high dimensions, right? Otherwise, why do OpenAI, this text ADA embedding gives you only like, 768 dimensions? Why can't we just scale the bird to like 7,000 dimensions, right? So there must be a catch here, right? The catch is, we will come to that later, but let's look at this example, right? So this is a very simple regression problem, right? So you have a bunch of points there, and they want to draw a line somehow, like pass through all the coins and bestly describe how the trends look like. Regression problem, a classic regression problem. Usually a classic regression problem is, we use a polynomial function to kind of feed those points, right? So we can gradually increase, so we can gradually increase the number of parameters here. So we see that the right curve is more and more feet to the data points, right? So that gives you less error. This mean error is actually becomes lower and lower. So your model is more and more descriptive on those data points, right? And so as we increase the number of parameters, you get more freedom, so your model becomes more powerful. And this is basically means that higher dimensions means you have more parameter to tune, and more parameter to tune means you have more freedom, more degree of freedom of your model, right? And therefore, your model becomes more representative, and therefore, it is easier to use this model for downstream tasks. Right, so this is a logic chain behind, and this is also like a very extreme case. If you don't define the like the number of freedom, the degree of freedom in advance, you just define the degree of freedom is always equal to the number of data points in your training data. Then this comes to the Gaussian process, which is a very classic way of doing non-parametric Bayesian. And then in this case, basically every data points that you see here is basically a parameter, right? So you can feed a Gaussian distribution on every data point. Then eventually it is very powerful to represent any kind of trained line, curves, and so on, right? I think in the quant field, right, people use this kind of Gaussian process to let's say 10 years ago, people use this Gaussian process to model the stock price and so on. Right? So it's very powerful nonlinear regression method, right? Because it has a lot of parameters, right, to feed. And for those like want to go to a little bit theoretical, so there is a very classic concept in the machine learning called VC dimensions, which basically defines, if you scale the number of parameters to infinite high, you can basically do anything, right? So that's basically what intuitively VC dimensions mean, right? And many of you may see these T-shirts, either on Instagram, not so often, right? But on LinkedIn, on Twitter, on in the academic conference, right? As you probably see this T-shirt, but this is also because of the previous logic chain, right? More parameters give you more freedom. More freedom makes the model more descriptive on the data, right? So that's why you see back in 2022, right? So there was people just say that, okay, so as long as we add more parameters to the deep neural network, so everything can be solved, right? So everything can be modeled, everything can be memorized, and so scale is all you need, all right? And but of course, we know that this is not true, because if you add more and more dimensions, not only it is adding the cost of storing, computation, and so on, but also like it makes the model even more data hungry, right? I heard that by training this GPT-4 or this Llama, whatever, this large language model, we have already consumed pretty much all the human data that we have already, right? So what happens if the model just needs more data, right? What can we do, right? We don't have more organic data anymore, right? Human labeled organic data, or it's very expensive to provide new data to feed the model, right? So basically everything that is from now on created by human is going to be just a food that we want to feed to the large language model, because they are very data hungry, right? Okay, so let's back to the topic that embedding space should be dimensionally adequate, high but not too high. Oops, did I miss something here? Okay, I think I didn't finish this slides. I think I was like get distracted by something, right? Okay, anyway, so now back to the high until now. Oh yes, now I remember. So high but not too high. So we just see, I just basically show this logic chain to say that, okay, the higher dimensionality usually give you better performance, because the model is more powerful, more freedom of degree, and more representative. But why not too high? Right? So because this is closely related to downstream task. So let's look at this coin case again, right? So we have this, each coin has some very, specific parameters, specification, diameter, thickness, and weight. Let's say we want to build a coin sorting machine, right? Let's say if you have keys, the keys always want to sort the coins in a very smart way, right? And then should we leverage these 3 dimensions to to build a coin sorting machine, right? Actually, we don't, right? So this is how the coin sorting machine looks like, right? So basically, you can see it doesn't leverage the other two dimensions. It just leverages the diameter. That's it, right? I mean, the gravity just do its job, right? So otherwise, the thickness and weight is not even playing any role here, right? So that means if you want to build, if your downstream task is about sorting the coin, right? So putting the coin into different bucket, you don't need the other two dimensions. So there's no point to represent a coin into three-dimensional space because you don't need that in the downstream, right? So that's why I say it should be adequate, it should be high but not too high, sufficient, right? If you don't do that, right? So let's say you build a coin sorting machine. So this is something that I ask ChatGPT to generate it with DALL-E, right? I say you have to be very, very sophisticated. You have to understand, all the kind of specification of the coin, and then try to sort them into different bucket. And then this is the machine that ChatGPT gives me, right? It's very complicated, right? So there you can see there's a thickness, weight, color, probably using computer vision to kind of detect the shape, all the kind of things, and then eventually you have a very complicated machine, right? Yes, so I would say the dimensionality should be enough for the downstream task, sufficient enough for the downstream task. So I give a lot of intuitive explanation about how the good embeddings look like, how the bad embeddings look like. But if you really want to dig deep into this topic, so I highly recommend to look at this paper, to read this paper. Is Understanding Contrastive, blah, blah, blah. It's some paper written by MIT guys, so just trust in the result, right? So it's give you a lot of theoretical bounds and on the embedding, how the hypersphere should look like, alignment, uniformity, and so on, right? Okay. So the next question is, what can be embedded? So we know the text. Some people heard this word-to-vec, doc-to-vec, right? Sentence embedding. So we know that the text can be embedded, but eventually, in fact, everything can be embedded, right? So, for example, if we talk about image embedding, so we can use ResNet, later use Clip, all this model to embed image. We can embed video, audio, 3D mesh. The embedding model can be also multi-model. That means you can input two different modalities into one embedding models, and it just compress everything into one vector, right? So, for example, a PDF there could be a PDF embedding model because a PDF includes both text and images, right? HTML sometimes includes even more, like source code and so on. And there is also a game scene. If you play with Unity before, you look at the Unity asset package, you can see that in the asset there is actually a lot of multimodality resource there. There's 3D mesh, VFX, the visual effect, and the image particle effects and so on. That's script, right? So it's really like if you do game development, you'll know that Unity really handle a lot of multimodal data, right? So even the embedding itself can be embedded, right? So it's kind of compression, dimensionality reduction, distillation. These can be considered as embedding the embeddings itself, right? So yes, so there are some tables here. So I'm not going into details. If we just focus on text embedding, right? So there are subdomains such as you can do language-specific text embeddings, right? You can do bilingual, multilingual embeddings. You can also work on low-resource languages, focus on the transferability of the languages between, within the same alphabet or across the different alphabet, right? And there is also domain-specific embedding. So, for example, in the company, that I work with, right? So a lot of legal company, legal tech company asking for, kind of a fine-tuned embedding on the legal domain, right? And also on the medical, right? Medical domain. Right? Those are the domain-specific embeddings that you can work on, right? So there are a couple of also right now the challenges in the whether in the application or in the research field of multi-embeddings is, first of all, how do we handle the multimodal embeddings? How do we map different modalities into one embedding space and make makes things searchable, right? Makes things comparable. For example, audio, image, 3D, text into one dimensional, into one coherent space, right? And the other is how do we handle very long context, right? So previously, if you remember, BERT model only supports 512 tokens as input length, and but now you remember like GPT-4 supports up to 16K, right? 16,000 input length. So what about the embedding models, right? Can we put more and more data into embedding models without losing the kind of without having this whitening effect? So whitening effect means that you put too much information into the embedding model, and eventually it just looks like an average vector, right? It's just whitening into a kind of white noise. There's no information there, right? So how can we prevent that? So this is also a topic, a research topic in the embedding world, right? Okay, so those are the kind of the general information about embeddings, and then now it comes to the kind of the buffer, the bluffing part, right? So how great Jina Embeddings is, right? So we released Jina Embeddings V2 version 2 back in October 28th, right, last year, right, and was immediately ranked on the Hacker News for 1 day, right, on the top #1 position for 1 day, and there are a lot of discussion, a lot of upvotes, a lot of people criticize us, you know, but haters gonna hate, right? So this is but eventually it has a lot of impact in the community. You know, people react very greatly positively on this, you know, using our embeddings everywhere. And we have, up to today, we have achieved 1 million downloads on Hugging Face in 2 months. Right? So why our embedding, that means there are a lot of embedding models in the world before us. Why Jina Embeddings was a big deal back in October 28th, right? Because it is the world's first open source 8,000 token length embedding model. It's really the first open source. Before that, there is only OpenAI's text embedding ada-002, right? So this is a only embedding model can support 8,000 token length, right? Other embedding models only do like 512. And we also did it in a completely open source way. So we open source the training code on GitHub, model weights on Hugging Face. We wrote a research paper and published on EMNLP conference, and also uploaded to archive. And our training data is also available on Hugging Face. So this is what Annie previously said. So when you consider open source AI, so it is not as simple as just open source the source code, right? So AI is more than just source code. So the data, the procedure, you know, how do you tune, fine tune, all this kind of stuff. It's very important, right? So in order for other people to fully reproduce your result, you need to kind of open a lot of. You need to be like a very transparent than just releasing or just uploading your source code to GitHub, right? And the other reason is, of course, I mean, open source is a good merit, right? But of course, it has to be very good in the performance. So it is also has on-par performance versus OpenAI's text embedding ada-002, right? So the kind of the performance is really close, right? Text ada is back in the days it was 60.99, and ours average score on 55 tasks is 60.38, right? So it's very close. And later we get some review from kind of like another startup based in Bay Area. It's Llama Index, which is basically kind of the startup work on the RAG solution, search using embeddings and so on, right? So they evaluate our embeddings versus other open source embeddings versus other commercial embeddings such as OpenAI, Cohere, Voyage, Google's embeddings, and with different setup, right? So this re-ranker, with re-ranker, not re-ranker, this is kind of the a special kind of configuration in the RAG, this retrieval augmented generation setup, right? And then eventually they found out our Jina AI base embedding is actually, if you look at this red row, all right, so it's actually the best one in the under the BG re-ranker and Cohere re-ranker. Right. So their conclusion is, in summary, to achieve the peak performance in both hit rate and MRR, the combination of OpenAI or Jina AI-based embeddings with Cohere re-rank or BG re-rank large, re-ranker stands out. Right? So this is a conclusion from the third parties, right? So not from ourselves. Right? And then there is another one, happens just recently. So this one was in November last year. And there was another one from recently from Stanford, this HII local. So they basically built another long embedding models which supports up to 32,000 token lengths, right? So this is 4 times larger than our embedding models, right? So they also built a new data set to evaluate whether this long context embedding model really does well on long context, right? So basically to solve the kind of misconception that if the context is too long, then it has this whitening effect that eventually everything becomes white noise, right? So you only get average information from the long context, not very representative, not very useful, right? So in this comparison, okay, so we are not, to be honest, it's not the number one. But if you look at our model size, okay, so model size is also like a bigger, right? If you look at the fine-tuned on this column, right? So you can see that the top performer model, like M2 Bird, the 32K, this is actually fine-tuned on this data set, right? But our model is actually not fine-tuned, right? So we basically compared zero shot versus their fine-tuned model. So which is a little bit unfair, but we take it, right? Because we are in the top 5, right? So yes, so in the top 4 models, like these two are fine-tuned, and this E5 Mistral 7B Instruct, this model is actually very interesting. This is an embedding model, but it's actually trained from the Mistral large language model. Right, it's using large language model as embedding models. That's why you see the parameter size is terribly huge. It's like 7 billion versus the other is just like 100 million. Right? So this is because it's Mistral model actually. Right, so that's why it has this very huge parameter. Right, but again, if you look at that. Look at it in this way, right? So how do I justify we are the best, right? Because these are the two are fine-tuned, so they cheat, right? And this one is a large language model, so they have very high degree of freedom, right? Remember what I said? So if you have more parameters, then you have more representative model power on the data, right? So in this case, right, under this narrative, then we are the best, right? Which is like the fundamental things that you have to do every day as a CEO, right, to the investor, right? To kind of build a lot of imaginary scenarios. Anyway, so the conclusion is Jina Embeddings V2 is actually, like strictly speaking, was the best open source 8K embeddings in the world, right? So how did we train this V2? Actually, there was a lot of hard work, right? It's not about all this like light-hearted jokes, right, that I'm talking today, right? It's actually like a lot of work, GPU money that put into this stuff, right? And so we actually have 2 versions. The first version was not that great. We published the first version in June summer last year, and was not really like nobody really cares, right? Because it was very average performed, right? Mediocrity, right? And then later in the version 2, we actually hit a lot on Hugging Face and also Hacker News and so on. Right? The architecture is there's no mystery. We basically modify the BERT, right, by using some kind of technology called alibi, which kind of extend the context length to arbitrary context length by modifying the positioning encoding or something. Right? And there was a training step. Is basically we first pre-train the modified BERT, so scale the BERT model to 8,000 tokens, and then fine-tune with our collected text pair. So we also pay some money to buy high-quality data. So as Annie said earlier, that good models probably like very similar to the on the architecture level, right? So if you look at right now the open source large language models, most of them are based on Llama architecture, right? So we are kind of the same in the embedding world. Most of them are based on BERT models, right? BERT encoder models, right? So, but what makes really the difference is the training procedure and the quality of the training data. Right. So here we do two-step fine-tuning. First, we fine-tune with the text pairs, and then the hard negative, which is basically the triplet. Right. And earlier this year, just January 15th and January 9th, we published two bilingual models. One is German-English models. The other is Chinese-English models. Right. So this bilingual embedding models allows you to search using German to search English and vice versa. Or you can also, of course, use German to search German. But you can use German to search English, English to German, English to English, English, German to German, right? So like a four-way journey. And so the performance is also on top, right? So because this is basically on top of our foundational 8K models, we fine-tuned, we retrained the model for this bilingual retrieval task, right? And so this is, we also set up, and we also noticed that there's actually no kind of embedding evaluation in the German language. So we also established this MTEB Deutsch for this evaluating the German embeddings. There is one German embeddings provided by Telecom. And it's actually a Deutsche Telekom, but it's actually not so good, right? The most competitive one is actually from E5. E5, I guess, is from Microsoft. It supports multilingual, but the model size is much, much larger than our embedding models. Right. Okay. So finally, how to use embedding V2. So the easiest one, or not the easiest one, the geekiest one, right? So it's using Hugging Face, right? So you can, because it's open source, you can go to our GitHub or directly go to Hugging Face and then look at this search for Jina Embeddings V2, and then you will find out like a lot of we curate a lot of collections for your usage, right? And there, you may even find out some like secret embedding models that we haven't published yet, right? The other easier way is to use our embedding API, which go to this URL, Jina.ai/embeddings, and then you can just use it, apply an API secret, and then do the curl stuff, JavaScript, and so on, right? If you are like an enterprise user, you probably don't want to use API, but you are also not very kind of lazy to use open source one, right? So then probably you want to seek for this AWS on-prem solution. If your company use AWS internally for all the computation, all these things, then you can go to the AWS marketplace to find, our Jina Embeddings V2, German English one, and also Chinese English one. Right. Otherwise, if you are neither of the above, but you are using some kind of rack solution, or you are trying to build some rack solution, either using MongoDB, Quadron, Pinecone, Chroma, VVL, all this vector database, vector stores, or Llama Index, Longchain, Haystack, this rack solution, you can also find Jina Embeddings on their documentation page. So they have native support of using Jina Embeddings inside their framework or inside their products. Right. Finally, we actually have a nice poster about the embeddings revolution, and we also sell this as a product, right? So basically, you can, if you really like embedding, you say, "Oh, Han is so great. This talk is so great, and I love embeddings. I want to put the embeddings evolution of the embedding into my living room, and I want to look at it every day, right?" And if you are like that, right? So feel free to go to our website and also buy a poster from us. Yeah. Yes. And so with that, and that's the end of my talk. And thank you.
Thank you, Han. I have to say that for the founder who raised 38 million euro, you're admirably focused on coins. Yeah, we can start with the questions.
Cool. Thanks for the talk. It was super educational. Really like how you explained everything. I have a more technical question. When it comes to like double descent phenomenon, do you think that using LLMs already goes into the second descent idea, and you basically can just over-parameterize the embeddings like crazy, and then they will still work again because they get, implicitly regularized because you're in the second descent part? Do you think that is the case? Has that been tried? Is there any research on that? Does it work?
You mean you're afraid of this hype is going away, right? I think it is. I started work on AI since 2009, right? So back in the days, it was very. It's not really AI. It's just machine learning. People call it. So now I see that okay. So people call it machine learning because it's very stupid, right? Because it's based on a lot of things are based on parametric Bayesian models, right? And so you have certain parameters inside your models and you feed to your data, and then you can do very trivial stuff, right? Like a document classification, and that identifies the topic of a document, whether it's political news, sport news, and so on, right? Or recognizing the noun-verb from the sentence, right? I think this round, like with large language model, I think it is really kind of impressive to me, right? I've been working in this AI for 15 years, and this is the first time as I was like really surprised by the performance of the AI, and I really use it on daily basis. So I think this time the trend or this kind of hype comes more solid than before. Right.
Sir, I think I might have like misspoken. Just to clarify what I mean, there's this ongoing phenomenon theory that if you keep on parameterizing the models and adding more and more parameters,
yes,
at some point, instead of regularizing it, they will instead of overfitting more and more, you get implicit regularization because you just add more parameters. So
I see. So you're basically asking on the technical part.
Yeah, it is a very technical question.
Yes, I actually usually with more parameters, you need to add more regulations. So I'm not really familiar with adding more, using this kind of intrinsic properties to kind of self-regulate doing the self-regulation, right? So usually, I remember back in the days, we were talking about this L1 regularization, L2 regularization to make the model sparse, all these kind of things. But I'm not seeing this right now very often, right? So except that recently we have this, or 2 years ago, we have this LoRa, low rank approximation, which kind of a little bit leverage the regularization and the low rank matrix property. But otherwise, I don't think the sparseness is, sparse machine learning is still there. I don't know. Yeah.
Hello, I'm Jonathan from Wikimedia. I have 2 questions, but one is, so I come from data science. I'm comfortable with topological transformations, but now I have to explain to pseudo-politicians about why an embedding is a valuable asset for our organization, and without using the word matrices. So I think that's a good expertise you have. How do you explain the value of embeddings to, and in your case, investors or otherwise decision makers outside of tech?
Yeah. This is actually a very valid and hard question. Actually, it is not. So first of all, the conclusion is it is not easy to explain the value of embeddings to the investors or to the customers, because usually the customer wants a solution, doesn't want a subcomponent of the solutions. Right? So the embedding, no matter how good it is, it's just a component. It's a very important component, very important piece of this system, but it's not the system. It's not directly answer the question. So this is a kind of the challenge that we are facing, the sales marketing team at our company are facing when talking to potential leads, customer, and so on. So usually what we do is we combine the embedding with applications, with certain downstream applications. The one typical one is search, right? So you can, once you have the embeddings, you can look for the most similar items that in your database, in your knowledge base, you can retrieve the images that look like the queries, right? So you want to found the kind of, let's say, for the e-commerce company, you want to build something like a shop's look, right? So you take a photo of something and then you search in your stock articles about things that look similar, right? With embeddings, you can solve this very easily, right? The other things that we can work on is you can also get some inspiration from those vector stores, vector database company, right? So in Berlin, we have Cloudgeometry, which 2 days ago, they just raised 28 million for Series A, so congrats to them. And then you can also look for MongoDB, Vivian, those vector database company, look for the solutions, documentations, how do they kind of market themselves, right? How do they justify their value proposition to the market? So this is often like the market still needs to be educated, right? This is also something that I found very interesting, that we spend, I started to work on neurosearch since, embedding this kind of technology since 2020, right? But before that, I was also doing that back in Zalando, also back in Tencent. I was also doing this embedding stuff. We spent years to educate market about embeddings, but it's very, very, it's not very progressive, right? Well, ChatGPT only used 1 year, and then this large language model is now everyone can talk about this, right? I think this is also because this application on the application level is much, much more intuitive to use large language model. It's kind of in and out, right? The in is natural language in, and then natural language out. So it's very, very direct. So I hope that embeddings we could find like a more kind of like intuitive applications for embeddings and also more valuable applications. Right now, we're also combining embeddings with a RAG system, right? To justify our embedding is a very important piece in the RAG system. But also, let's say, to be honest, like people, clients, investors will also argue that, okay, so it is a very important piece in RAG system, but don't forget that RAG also contains a re-ranker and LLM at the end as kind of the aggregator or like a consolidator, right, at the end. So then people ask, okay, so why don't you work on the large language models and so on, right? So this is but I think for startup, for startup like us, we made a choice to work on the embedding models instead of large language models, right? So there are a lot of reasons behind that. One of the reasons is probably we are GPU poor, right? That we don't have so many GPU. We recently just bought two, spent $500,000 on these 2 GPUs, and but in the end, we don't have so many GPUs to work on the large language models, and also even for the large language model startups, they also looking for. They sounds cool, right? They sounds okay. I have my own large language model training from scratch. It sounds very cool, but eventually they need to commercialize those large language models. They need to find a high-level applications that can support their cash flow, right? And on that day, so they probably won't be that cool, right? In our case, we focus on embeddings also because this is kind of a little bit niche market that the competitor is not like the big players are not really kind of paying attention to, and this gives us some space to develop, to kind of focus on own thing and also develop our clients, right?
I have a narrow follow-up. We're tasked with making a vector embedding for Wikidata, and that's 300 languages. Is there something that Jina does for that?
Yes. So we actually, this is also another design choice that our team made. So we first work on the bilingual embeddings and then on the multilingual embeddings. And the reason is twofold. First of all, when we talk to the clients or when the clients approach us, they claim that they need a multilingual embeddings. But in the end, they just need their mother tongue plus English, right? So let's say German companies approaches us and they say, I need a multilingual, but in the end, it's just German plus English. And the Chinese company are also the same. The reason behind that is not so many companies are like big enough as Amazon, right? So they only have the clients for these countries, right? So usually their domestic market, and then plus U.S. market, right? So that's usually a good company already, right? And a lot of companies just like focus on one country only, right? Until like on December, like I visit. I had a conference in Singapore, and I realized that they have 4 kind of languages like people speak there, like Indian, Malaysian, Chinese, and English, right? I realized that, okay, so multilingual is actually pretty valid if you want to be a general purpose model in that country, right? So this is kind of valid. And the other reason that why we don't work on multilingual first is because the data is hard to get, right? So it's very hard to get like alignment, like aligned parallel data, right? Parallel text data for multilingual embeddings, right? But what we can do is right now we have these large language models which can serve as a generator. We can use synthetic data. We can also leverage. So for example, right now we have German English embedding, which is very good, and English Chinese embeddings, which is also very good. Then we can use English as a proxy language to kind of transfer the knowledge in between. But then this involves some theoretical explorations there. Right.
We have linked and parallel 300 languages if you want to try it.
Oh, so that's good. Yeah.
So previous question was how you explain to investors importance of new embeddings. I have a similar question. How do you explain to investors making money on open source?
Oh, yes, yes. So this is also very good. Yes, it's always hard to convince investors, right? So we have been raising money for 2 years, just for you to know. So, just for you to know. And but it's, for open source, I think like open source also changed a lot, right? So we consider like our company was founded in 2020, right? In the days where commercial open source was defined in another way. It's not defined or driven by the AI companies. It's actually driven by cloud native companies. Back in 2020. So back in 2020, if you remember that all the startup, they somehow have to attach to Kubernetes, right? You have to say, oh, we are the kind of Kubernetes. Their software packages always start with K, right? Yeah, microservice, orchestration, right? Orchestrator. We have all this K native, all this stuff, right? Hello. Oh, I think this is like dead. Yeah, but then there was certain like a kind of role model. Oh, thanks. There were certain kind of role models that you can follow, such as MongoDB, Elastic, right? Datadog, right? So those are the companies that you can see as a kind of role model in the cloud native world, and then you want to follow their successful path, to copy their successful path, to kind of lead your way, right? But I think there are a lot of things change in the open source world since AI jump in, right? So the very foundation, the very definition of open source also changed, right? Like you can say OpenAI ruins the word of open, right? So they basically replace the concept of open source to open access, and everybody is still fine with that, right? As long as you give me a very powerful model, give me a very powerful model that I can for free to use, right? It's relatively fine, right? Replace the concept of open source to open access, right? And things develop also very fast, very like in last year. But in general, the idea of having commercial open source software as a company is that you want to have a very broad community, developer community, so that later you can kind of convert this community into some paid users. Right, so you basically focus on the technical impact. You focus on the developer experience first, because eventually, the decision maker also ask the developer's opinion about their user experience, about their comments on certain technology. Right, if your technology becomes a kind of the cornerstone of their system, right, and then there's no way for the company to escape you from their application, from their system integration and so on, then the company will come to you and ask you, okay, so looks like you guys are pretty successful in this open source software, right? Do you offer some kind of first cloud service, right? Do you offer some cloud service that I can directly use somehow, right? Better version, professional version, right? So this is usually, this monetization strategy is usually what we call like a free infrastructure and then value adding on the cloud, right? So basically you provide infrastructure, all the software, source code infrastructure for free, but then you build a wrapper, like usually a UI, right? Combining with a UI to wrap your infrastructure with a nice UI and then cloud scaling, a zone, you can geolocation, all these kind of optimizations, and then provide this as a professional cloud service to the company, right? And the other is, usually this is a part where you can introduce SaaS, subscription-based model and quotas, all these kind of things. The commercial, traditional SaaS companies, what they do, you can introduce them to your product, right? And the other is, of course, professional service, right? So if you look at Elasticsearch, I remember the revenue model back in 2020, 70% come from the cloud service, and then but still like 20% comes from the professional service, like including the kind of customer service plus training, right? There is also a training that you have to apply for Elasticsearch certificate, right? So they also made some money there, right? So in total, that professional service, like 20% of revenue, yeah.
I think Elasticsearch is a very bad example. So actually, just to summarize, besides posters, how do you make money right now on those embeddings?
Yes. So right now we basically we build embedding as a SaaS service, and so basically people pay as you go. To pay us, and then also there is another way is on the AWS marketplace. You can also charge people by the hours that they use your embedding models. Right. So these are the two ways that we monetize it. But besides that, right now the embedding service is not the core revenue of our company. Our core revenue actually comes from the prompt part, which is I showed in the early slides, but I didn't explain today. It's actually from prompt engineering, prompt optimization. There, the market is much bigger. Because it is more like a power user market. So as long as you can use computer, as long as you can use ChatGPT, you are a potential buyer of a potential client of our product, right? But for the embeddings, even though we have SaaS, right? So we have this API, you can pay as you go, bound your credit card and so on. But I don't believe this is will become the main revenue driver of our company. I think it will still be like a working with kind of big companies, like either like kind of they build as kind of strategic partnership, and this is what we are exploring right now, or exploring some revenue sharing model. Right. So one example is, for example, we are working with a lot of vector database and also traditional database company to build a revenue sharing kind of entry point. So in their vector database, you can, in the drop-down, you can select different embedding models, right? But if you use us, then we return like a 50% of the revenue back to you, right? So this basically is kind of win-win for both vector database company and also for us, right?
When did you start monetizing?
Since last year, yeah.
Not a different kind of follow-up then. Do you think embeddings will ever or soon become useful in tabular data, or not really needed there?
Yeah, I do think. I think like tabular data is definitely like something that is like eventually like the future is multimodal, right? So modality includes tabular, 3D mesh, image, and so on, right? I think, but to be frank, our company is right now not working on tabular data. So the next model will be the 8K lens plus image. So it's kind of a clip model, but it's an improvement over clip models, right? So we work on that, and then there is also like we will also include kind of different languages, including the programming language, into that model. But as I said, the tabular audio data, this definitely is the next step. Yeah.
Thanks. What was the computational cost of your big and small models, and what do you estimate to be the computational cost of fine-tuning on your model B?
Yeah, I think if you consider the try and error, right, then basically I would say since in 2023 we have spent like say maybe 2 to 3 million on training those models, like including the experiments and so on, which depends on the results and the company size. You can either say it's big or small, but it's basically a 2 or 3 million, right? And so the fine tuning cost. Well, right now we don't have. We used to have a fine tuner project, which is also open sourced, but it's kind of too old because it doesn't support the 8K context lens fine tuning. It only supports middle-sized models, and so right now we are working on like kind of improve the fine tuner a little bit, right? By introducing like a synthetic data, automatic synthetic data generation. So in the end, you don't have to feed your own data. You just say, oh, I want this embedding to be good at to be good at legal documents. That's it. You just give an instruction. And then you later wait for half a day. Oh, of course, give me your credit card, right? And then I will return you a fine-tuned model after half day, right? Something like that. So this is basically what we are working on right now.
Sorry, did you use cloud-based GPU or TPU?
No, we actually bought, and then we actually put the. We try to. We have physical machines, right? Okay. And then you have to find a place in Berlin which is safe enough to put your GPU there, and then it has enough power. And then later we found out, it's cheaper to put this physical machine into Scandic countries somehow, right? So right now, next year, this year we will probably move to Stockholm, right? Put this machine to Stockholm. I don't know why, because probably the electricity bill in Germany is like a little bit high.
You're using them as heaters.
Yes.
Thanks for the talk. So I have a question, maybe a little bit of follow-up on your fine-tuning service that you are still developing.
Yeah.
So we have a very, very big data set. It's very highly annotated data set. And we are looking to train some models on it. And if you are looking for maybe beta customers or guinea pigs to try your fine-tuning thing, we come with our own data, and these are, this would be a use case for us because we're looking into that. Then the other question I have, what's your intuition or any empirical observation that you had regarding the context length, the vector size, and the amount of data? So assume that you have a huge amount of data, very deeply annotated, and you can describe this data as a document which is very long, and then you would have a very big vector. Or we could break it down into like feature value, like p-value kind of thing, and train on a smaller size of vector. But we care the most about maintaining the longest context. So what's your intuition, or what would you try in that direction? Would you go for 1,500 dimension vectors or a 300 dimension vector and train with massive data?
I think. Okay, so I think this is a very, very good question. Depending on who do you ask, right? If you ask a vector database company CEO, they will say, chunk your data as much as possible because it will actually generate a lot of vectors. And since we are storing those vectors, so it's like we made a lot of money, right? And but if you ask me, right, then I would say so. First of all, like the number of parameters. So whether you want to serve or publish small base or large model highly depends on your economic capacity, right? So let's say I only have this GPU, I cannot really train X large model. I can only train a base model, right? Then I have to basically fix the parameter size in front. I know this is my capability, right? This is my capacity. I know if I increase the parameters, I probably have to delay the release of the model. And I only have this GPU, so this basically already restricts the size of the practical number of parameters. So this is the first part, and then the second part is the context length. Whether we want to further push the context length to an extreme, and the answer is actually. Yes, for the embedding models. So we do want to have. So you can basically think of embedding models as a compression algorithm. We do want to, just like when you use zip, right, in the on Mac or on Windows, right? You just want to double click, right click on your file, no matter how big this file is, and then you just say compress into a zip file, and then it does this compress, right? And we also want to do this compression as for the embedding models, right? We want to compress as much info losslessly, right, into a fixed dimension vector, right? So this is this is very true. We do want that, but the problem here is actually not about the embedding. So there's one guy previously asked, okay, so what are the applications? And I says RAG, right, retrieval augmented generation. The problem is that if your embedding model supports like a 16K context window, right, but the re-ranker doesn't, then it is useless. So right now the re-ranker does not support very long context. The re-ranker, most of the re-ranker are based on bi-encoder or cross-encoder, these kind of things. They only support up to 500 tokens length, right? So because you first retrieve the documents, right? Okay, so you encode the full documents, 8,000 tokens to one vector. So you retrieve the documents, but eventually you have to re-rank them, right, to get better precision, recall, this kind of thing. So when you do the re-ranking, you have to put query and documents together into the model. But the re-ranker model doesn't support long context length, right? So therefore, the next thing that we are working on is actually to provide 8K re-ranker model. Right. So now we have 8K embedding models, we have 8K re-ranker model, and then we have 8K, at least 8K LLM, right? So most of the LLM right now supports 8K, right? So now the full RAG pipeline can be, let's say, reimagined, right? Because previously, like there is a bottleneck in the embedding model, there is a bottleneck on the context length in the re-ranker, so we can only do chunk, chop to store everything into the vector database and then do the things. I believe if we can eventually, for every document, no matter what it is, right, whether it's a big image, super resolution image, or whether it is super long document, no matter what it is, if we can always represent them into a one fixed length vector, then the design pattern of the search team will also change. A lot of tricks, heuristics that we have right now in the RAG system, re-rank, top K retrieval, this kind of things, and sort will also be changed. Yeah.
Han, thank you very much. Thank you guys for your questions.